to build the model and train and test the model. I'm sharing the screen with you. I request all of you to please open Google Colab. Let me rename this notebook. We are building VAE on MNIST. So to start with, I hope everybody is on same page. Let's wait for 1 or 2 minutes. Everybody start the Google Colab and start writing the code. I hope everybody has opened Google Colab and created a new notebook. Let's start with importing the important libraries. So first of all, we will be importing. Just give me a moment. Fine. Sorry, I got an urgent call. Uh, let's go back. Let's import the important libraries. So firstly, we will import TensorFlow as TF. Then we can also import the layers. TensorFlow dot keras, and then import the layers. Import layers. And also we will need the NumPy. So import NumPy as NP. Then matplotlib, of course. So import matplotlib dot pyplot as PLT. This is same what we have done yesterday. So we have imported TensorFlow, NumPy, matplotlib, and then let's start executing it. Meantime, I can write a new code block. And the first step is downloading the dataset. Here also we are performing this experiment on MNIST dataset, which is very simple, and the size of the images is very small. So the lesser computation is required. That's why we have chosen the MNIST dataset. So the first step is load the data, load and pre-process the data, and you are already aware that what we have to do in pre-processing. Pre-process and next data. Right? So I think everybody is aware what exactly is how do we download the data. We can use the same function here. Now what I'm doing here is I'm not downloading the Y label because we don't need that. Since I told you it's an unsupervised model, so we do not need the labels for training. So I'm just interested in the input X for training. So I'll only download or only copy. Of course, Y label is also available there, but I'm not interested. We are not. We don't require Y labels. And then we will download or copy the X test. And of course, in test, to evaluate, we need Y test. We should know what is the exact label. And if you can recall yesterday's code, we use tf.keras.datasets.mnist, and then the function load data. This is what we used yesterday as well. Right. So this statement helps us in downloading the MNIST data. We are copying it into these three variables. We are not copying the Y-train data because we don't need labels here because it's an unsupervised kind of function model. Then, of course, we will normalize the data. So X train is equal to X train, and consider this as a float variable. So I'm defining it as float 32, and I'll divide it with 255 because the pixel values are from 0 to 255. That's why I'm normalizing it by 255. Similar thing I can do with the test data. So I'm copying this above line and change the variable name from xtrain to xtest. Sorry, x underscore test. So we have normalized both xtrain as well as xtest. Fine. Now we need to reshape them. Today we will make this xtrain and xtest as 4-dimensional instead of 3-dimensional. Let me reshape it, and then I'll explain why we need this 4-dimensional reshaping here. I hope my voice is clear. There is no issue of low voice. So the next task is to reshape this. So I'll reshape using the np.reshape function. np.shape function, and as an argument I'll pass on, of course, the data which I want to reshape and the dimension in which I want to reshape it. So it's -1, 28 cross 28 cross. So I have made it 3-dimensional, in which the third dimension has only one channel. However, if it was RGB image, this value should have been 3. So here, since it's a grayscale, we have only one channel. That's why we have included 1 in this third dimension. This -1 basically tells this function that this is a default value. Any value can be fed here. So since this xtrain in this MNIST data set has 60,000 images, so by default it will take 60,000 in place of this -1. So -1 is not any fixed value, and we don't want to make it fixed. That's why we can consider -1, and the actual value will be considered here. We don't want to hard code this. And similarly, we can reshape the X test variable X underscore test in the same shape. Fine. So here this -1 will be replaced when this data is felt here. Data is already copied in these two variables, X train and X test. So this will be 10,000 because there are 10,000 test images here. Now, one more variable we want to consider here, that is the dimension of latent attributes. So that latent dimension will be, we are considering here as 2. At this, we will see when we will be visualizing the output of the encoder. So this latent dimension will be visible there. Now let's run it. Let's see. The data is downloaded. I think there is some error in data type float underscore 32. So this is not underscore. This is just float 32. I'm sorry if you have also faced the same problem. Just correct it as float 32. It's not float underscore 32. Let's run it again. Fine. So this has downloaded the data as well as done all the pre-processing on the training as well as the testing data. Now next steps is to build the encoder model. If you can recall our discussion in the previous session, I told you that we can build this encoder using CNN. So we will be using CNN here. So here we are going to define a function. Let's make a function for encoder. So as I told you yesterday, the syntax for making a function is def, and I'm considering it as the name of the function is build encoder, and we need to place a colon here. So that's the function name. Now in this function, we are building the encoder model, and I told you we will be using CNN to make this encoder. So let's see. You are already aware how we build a CNN. So firstly, I'll define the encoder inputs. What kind of input it is going to take. So encoder input, the dimension of the encoder input. So it is tf.keras dot. So I'm defining input in this format of tf. So I can define the shape, and the shape will be 28 cross 28 cross 1. So for one image, that is the dimension. 28 cross 28 cross 1. The 1 because it's a grayscale image. Here it was 4 dimension because this dimension was telling you how many images are there. Fine. So encoder will expect this type of input. So this input we will be using in one of the first layers. Now, first we are going to use the convolution layer, 2D convolution layer, and we can take the feature map output of any convolution layer in a variable. So that we are taking here. So x is equal to since we have directly imported the layers, we need not to write the complete statement tf.keras.layers. So we have directly imported layers. So layers dot, here we are going to use the 2D convolution layer. And as you are aware, what are the parameters, arguments we pass on to this convolution layer? Firstly, the number of filters, 32. The dimension, either you can define only one dimension. It will consider the second dimension as same for the filter. So it is 3 cross 3. Otherwise, the same way we can define 3 comma 3 as the dimension of the filter. And then we will define the activation. So activation is considered as rail here. We'll also define sprites. I'm going to talk now. So we will also define the strides. So stride is 2 here. Then we can define padding. Padding same means the same padding, no padding here. And so that's the argument. And then what input will go to this one, that we can define here. So that was the input which we are defining here. So instead of defining that sequential kind of model here, what we are doing is we define one layer at a time. We define input to that particular layer, and we take output of that layer. Now this output will be used as an input to the next layer. So again, we will use, we will have another convolution layers dot on 2D, and this time we are using 64 filters of dimension 3 cross 3. Again, we are using activation as ReLU activation. So the same syntax. Stride is also 2, and padding is same. If we are not going to define these two variables, it will consider default values of these. And here the input will be, can the audience tell me what will be the input here? That's the question for the audience. Can anyone tell for this particular layer what will be the input? Yes, the speed has given the correct answer. X will be the input. So what is X? X is the output of the previous convolution layer. Now we are making a sequential model here. The first layer, there is an output X. This output X will go as an input to the next layer, and this layer also is giving us an output X, which will go as an input to the next layer. Now we have used two convolution layer. Now we will be using a flatten layer. Flatten layers dot flatten, and as I was telling you, the output of the previous layer will go as an input here. And then we are going to use the dense layer. So X is equal to layers dot dense, and in dense we will define what will be the size of this dense layer, what kind of activation we are going to use here. And again, we need to define the input to this dense layer, which is X, and this X was the output of the previous. Either you can give different variable names here, but I think every time as an output of the layer, this variable, the output of the layers goes to this variable, and that we feed to the subsequent layers as input. Now, what we have done here, try to understand, try to visualize this. We have an image of dimension 28 cross 28, which is as input to the encoder. Now, this encoder consists of different layers. This input goes through these convolution layers, flatten layer, and dense layer, and finally we get these many dimensional output. So what we have done, we have reduced the dimension through this encoder, and this is nothing but the feature map. So we have basically done the dimensionality reduction with the help of this slip. Now try to recall the probability distribution. So for any probability distribution, we will need mean as well as the variance. So whatever features or latent representation we have got here, we will compute the mean and variance for that. So let's see how do we calculate that. So Z underscore is equal to layers dot dense, layers dot dense, and so basically what we are doing here is we are bringing this 16 output of dense layer to latent dimension, that is 2. So latent dimension, and the name of this particular layer will be ZME. So name uh, name is equal to Z underscore me. Fine. And to this layer, we are using name. We need this kind of inverted commas. And for this layer as well, we will give input as X. So basically, what we have two dense layers here. This dense layer brings the input dimension to this 16, and further this particular layer brings 16 to dimension as 2, and we have named this layer as Z mean, and this layer gives the output as Z mean. Now, second, we will have the variance layer. So Z underscore log underscore var is equal to layers dot dense, and we will also bring it to the same dimension. The name of this layer will be Z underscore log underscore var, and again we are giving the input as X. So these are kind of parallel layers. This input is given to both this Z mean layer as well as this Z log variable layer. So that is what we have done till now. We have built the encoder. Now there is a problem here. We need to implement that reparameterization trick, and so basically for that I need to write a different function, and I name, or rather I'll define a class for sampling, and sampling is nothing but that sampling layer which will implement the reparameterization technique. So let me write a comment here. So sampling layer for reparameterization trick. Try to recall our earlier lecture where we implemented the reparameterization trick. So we define a class, class sampling, and is one layer will go as an input to this sampling layer, and inside this class we will have a function call, which is nothing but the constructor of this class. So self, and then the inputs which we are going to this. And what does this function do? So we forgot to put the columns here. So after definition of class or the function, we need to include the columns. So inside this function, we will read the inputs. I'll tell you how this function will be used. Let me first define this function. ZMean is ZMean comma Z underscore log underscore var is equal to inputs. So whatever inputs coming here, that will be in the shape of this one. So we are populating these variables, Z mean and Z log variable, variance from the argument of this function. Then now try to recall that reparameterization technique where we were using epsilon or eta as a random variable. So I'll define uh, random variable epsilon, and for defining a random variable I can use this function tf.random and try to recall what kind of random function it was. So it was a normal distribution, and the shape of this variable will be similar to this z mean or z log variance. Why the shape should be same? Because we have to multiply that particular random variable with this variance. So the dimension should be similar. So tf.random.normal, and the shape will be, I can define the shape is equal to tf dot shape of z mean. Z underscore. I hope this is clear till now. And then the sampling layer, if you can recall that diagram of reparameterization trick where we were changing the value of z. So what we are going to do here is we will use this epsilon, and so basically this function will return z underscore mean plus z underscore mean plus tf dot. If you can recall, the formula was z mean plus multiplication of this z log variance and the epsilon. So tf dot exponential, and so it will be 0.5 multiplied by the variance. So the variance is z log variance, and it was again multiplied by the random variable epsilon. This is what we have done in the reparameterization. So I allow all of you to please complete this code. I'll just wait for 2 minutes so that you can complete the code. Let me run it if there is any error or not. So no, there is no error. So what we have done till now, let me summarize it again. We have included the important libraries. Why we need sampling, please explain. Fine. So sampling, don't get confused with the sampling. We are implementing this reparameterization trick. Fine. What is normal function? Normal function is basically you are basically creating a random variable which follows a Gaussian distribution. And with this class, what we are doing is we are just implementing the reparameterization trick. So if I think I'm already sharing, let me open that particular slide so that you can better understand that. Try to recall this PPT which is shown in the morning. Yeah. See this parameterization trick. What we have done here, we have considered this epsilon or eta, and then we have computed the new mean z as the combination of this earlier mean and this variance multiplied by this variable epsilon. Go back to the code. So fine. Now then we have downloaded this MNIST data set, done some pre-processing, brought it to a particular shape. We have defined a class for implementing the reparameterization trick. As an input, we are getting the z mean and z variance, and uh, then we are taking a random variable epsilon, and this epsilon is a random variable. Now, why we are using exponential here? Because we are considering this variance in as a log. Since this variance can take negative values, that's why we have considered it into log. And while multiplying it, we are using this exponential e raised to power this, multiplying it with epsilon. Now, somebody was asking what does this return? This return a vector here of same dimension of this one. Fine. Now, now we are going to use this sampling layer while we define this encoder model. What we have done till now, we have find out this Z mean and Z log variance. Now we will use this sampling layer or reparameterization here itself in the encoder model. And what we are going to do with that? So Z is equal to, we will use this sampling, and what we are going to pass to the sampling layer, uh, we will pass Z mean and Z log variance as a single input, because here we are, you can recall this input is copied to these two variables, Z mean and Z log. So in sampling class, we are passing these two values, Z mean and Z log, which we are taking here. Now, once this is included here, and in the encoder, we are going sequentially, two convolution layer, flatten layer, one dense layer, and then from this dense layer, we are computing two outputs parallelly, Z mean and Z log variance, and then we are passing these two input to the sampling layer to implement that reparameterization trick. And finally, this encoder model will return something. It's a function, so it will return something, ef dot eras dot model, and which will take encoder inputs and our Z mean, Z log, and the computed output of the sampling layer Z, and the name of this will be encoder. The name of the model will be what we have done. We have written a function for implementing the encoder, and whenever we are going to call this function, this will return a model which takes encoder inputs and gives these as output, and the name of the model is input. Fine. So we have defined this encoder model. Now, similarly, we are going to define the decoder model. So let's run it first. I hope there is no error. So there is no error. You all must run each of the code block and let me know if you face any of the errors here. Now, similar to the encoder model, we will, why didn't we use max pooling layer in CNN? So the idea here is we do not want max pooling layer. If you want, you can implement it, but that is not required. We are straight away reducing the dimension using this dense layer because we don't want to lose any of the information. There might be some information can be lost through max pooling. So we are considering the whole information, passing on the whole information. And then finally, we are reducing this dimension using this dense layer. You can recall the feed-forward neural network where we were when the number of nodes in the subsequent layers were lesser. So automatically, the dimension is getting reduced. Now, in decoder model, again, here in encoder model, we have used convolution layers, and in contrast to this, in decoder model, we will be using the transpose convolution layers. So the task of transposed convolution layer is upsampling. So basically they will upsample the input data. Recall the architecture of encoder and decoder. Encoder reduces the dimension, however, the decoder increases the dimension from the latent space. So here, instead of using convolution layer, we will be using up convolution layer, and the name of those layers is convolution 2D transpose. So now define the function name build decoder underscore decoder. In the decoder, we will define the inputs. What are the inputs here? So we are using latent inputs. Z will be the input here. So latent inputs, and how do you define those latent input? So these latent, we will define the dimension similar to what we have done in the encoder input. So here we will have latent input, and what will be the dimension? Can someone tell me? Keras dot input, and what will be the shape? What will be the shape? Can someone tell me what will be the shape here? What is the dimension of the latent? Yes, correct. So it will be latent for since the shape variable takes multi-dimensional. So we can just put a comma here and keep the next dimensions blank. We have defined the latent dimension of the latent inputs. Now what we are doing is we will use these uh, transposed convolution layers, and each layer will have some output and some input, so that input output will be x, and then I'm using layers dot dense. So we'll go reverse. What we have done in encoder, convolution layer, then flatten layer, then dense layers. Now in decoder, we will go reverse. We'll firstly have dense layers, flatten layer, and then we will use convolutional transpose layers. So in dense layer, what I'm going to do is, uh, let me first write the code and then I'll explain it why these dimensions are there. 64 and then activations. Activation is equal to reloop, and the input to this layer will be 8int underscore. Now you everybody know that the output of any of the dense layer is a single column. Now we have to convert the single column into a cuboid for inputting to the convolution layer. So basically our whole objective here is whatever input we are taking here, we have to convert it into cuboid. And finally, since we used here 64 filters, so the depth of the feature map output of this layer was 64. So basically, that's why we are using 64 here. And the size of the cuboid which we are going to make here will be 7 cross 7. So the output here was somewhere, I mean, it was of this shape. So we have to bring it back, this latent input dimension, bring it back to this dimension. So we are upsampling this output of this dense layer. And then we will reshape it. So we have used one dense layer to bring this dimension to this cuboid dimension. Till date, this dimension of this x is still a column vector, but with these many values. Now we will reshape this column vector to a cuboid. So x is equal to x dot reshape, and what we are doing here is we are making a cuboid of dimension 7 cross 7 cross 64. So 64 represents the number of filters which we have used earlier. So basically, ultimately, this the output of this decoder will be of this dimension 28 cross 28 cross 5. So that is what we are doing here. Uh, can we hold a second? I request all of you to please complete the code till now. Fine. So I hope everybody is able to write the code till here. So what we were doing here is the whole objective of this decoder is to bring back or reconstruct the input. So basically, we will go back from this latent dimension to the original shape of the input. So we have reshaped this input x to this cuboid 7 cross 7 cross 64. Fine. Now we will use this uh, 3D, transposed convolution layers, which will upsample this data. As of now, we just have blank data here. Now this convolution, transposed convolution will upsample this. So layers dot, and we will use on to the transpose layer. And what will be the argument here? There will be again 64 filters, each of 3 dimensions. So it's almost the transpose of what we did in the encoder here. So here again 64 filters of same dimension 3, stride, strides is equal to 2, and again activation will be ReLU, and padding is equal to same. And then what will be the input here? So the input will be fine. Then we will use another transposed convolution layer, layers dot on 2D transpose, and this time we will be using 32 filters. We call this first layer of the encoder. So I'll be using 32 filters of 3 cross 3. Again, the value of strides will be 2. Activation again will remain same. Activation is equal to value. And again, we'll have heading equal to same. And the input will be x, which is the output of the previous version. Fine. Now, what we are going to do here is we are considering another output. So the decoder underscore output, the decoder underscore outputs, and this time we are using layers dot convolution, 2D transposed convolution. We will use only one filter of 3 cross 3, and I'll tell you why this extra layer we are using here, activation, and this time we will be using sigmoid output. So instead of ReLU, we are using uh, the sigmoid layer, and this time the input will be. I think that's the output here. I hope, I think the screen is visible, right? Fine. So what we have done, we have built a decoder, and here we, as an output of this transposed convolution layer, will be based on this ReLU activation function, which will not be as per this range. So what we have to do is we have to use a sigmoid activation function here, and there will be only one filter, and we will be passing. This is doing nothing but this is passing each of these input, output of this layer values, and passing it through the sigmoid activation function. Now, as an output of this decoder model, it will return tf dot keras dot model. So this function will return a model which takes latent input as a latent inputs, which we define at the beginning of this function, and this gives us output as decoder output, which was output of this last layer. So decoder outputs. Then we can name this model as decoder. So that's where we have defined this decoder model. So let's run it. It has successfully run. There is no error. Now we have built encoder, we have built decoder. Now let us assemble them. Let us make an architecture which we can train. So we will make a VAE, a variational autoencoder. So we define a class VAE in which we will call these functions of encoder and decoder and some compile and fit functions. So let us, so what we are going to do here is construct with and define the loss. So what I'll do is I'll define a class in the name of VAE, and this class takes input as models tf dot keras dot model, and inside this class we will define this constructors. So def, by default it will be initialized with this function init. There are two underscore and init, and as an argument take self and this encoder as well as coder as input to this init function. Now inside this we define super function. I'm sure those who are not from computer science background, they might be facing some issues here with these syntaxes. But just don't get confused with that. You can directly use it. This is syntax related to definition of the classes and uh, defining the constructors of this class. So in the super function, we pass on UAE, then we call init function. So by default, whenever this class is initialized or object is created, this function is called, and this calls the encoder, and this assigns self.encoder the model which is passed similarly for the encoder. Self.decoder equal to decoder. Fine. So this was one function. Another function is the compile function. So I'll define compile, and as an argument, the self object will go, and optimizer can pass on to this compile function. As you can recall in the yesterday's experiment, what does this compile mean? So compile basically compiles the model which we are constructing, and inside compile we define what kind of optimizer we are going to use, and what metric we are going to use while training them. So inside compile, we will use the same definition, suppose VAE self, and it will call this compile function. Fine. Now, what exactly we do here? We define the optimizer. We define the optimizer here, and the optimizer is nothing but which we are passing as an argument to this class. Optimizer. Fine. And similarly, we will also define the total loss. So self, what kind of loss we are going to use? So it is self dot total. It's a variable loss tracker, and this we will define from tf dot keras matrix, and the name of this loss is total loss. Fine. So we have defined this init function of this class VAE. We have defined this compile function of this VAE. It is not necessary that we create class only, but this is the structured way of coding. So we have defined relevant functions of this class here itself, and you will get better understanding once we will use it afterwards. So now the third function of this class is training. How do we train it? So every step we are defining the train step. What will happen in each of the step of training? So train step, we pass on the self object and the data to this. And what exactly we are going to do here? We will see if is instance. Do we have instance of the data? We check it first. And if not, then we initialize this data from data 0. We can skip this part also. We are just post, yes, if there's no instance of it. Now, what exactly we are going to do here in this train step? We use this function of TF, that is TF gradient tab, gradient add TAPE. And what we are going to do here, we are going to use the encoder model which we have defined here. So let us see how to use it. So we are computing Z underscore. Try to recall what our encoder model will give as an input. So it's Z mean, Z underscore log underscore var, and the third one, Z, which we computed through reparameterization trick. And how are we going to call the encoder? You remember, the name of the model was encoder, and inside can pass on the data. So for encoder, the data will go as a input. Fine. Now, once we have used this encoder, so basically, what are we going to do during each step of the training? So basically, we will pass on the input data to the encoder, compute the latent attributes, and then pass on these latent attributes through the decoder and reconstruct the input and compute the loss function using the reconstructed output and the original data input. So next, we are going to compute the reconstructed input. So let me name it reconstruction. And how do we do that? We pass the latent representation Z to the decoder model. What are we going to pass on here? Can the audience answer this question? What will be the input to this decoder model? Z. Yes, correctly answered. Because why we are not passing Z mean and Z log variance? Can someone answer this? Why we are not passing Z mean and Z log variance? Try to recall that reparameterization trick. Why we implemented reparameterization trick? Because they were not differentiable. That's why we used the trick and computed this Z. So now we have calculated the reconstruction. Now we will define the loss. And try to recall, we had two terms in the loss function. One was the reconstruction likelihood. Another one was the KL divergence term. So we will define both of them. So firstly, we will define the reconstruction loss, and it will be so it will be TF dot reduce dot mean. Let me think. It will be fine. then tf dot keras dot process dot binary cross entropy. So we are in reconstruction loss, we are using binary cross entropy, and this reconstruction loss will be multiplied with the dimension of the input image, 28 cross 28. And then we will compute the KL loss. So KL for loss will be given as minus 0.5 into TF dot reduce dot, and here we are going to pass 1 plus z underscore log underscore f minus TF dot square of z underscore e. So these formulas are directly taken from those derivations. You can directly use them here. So for computing KL loss, I'm using the formula directly from those derivations. So it is 1 plus z log var minus the square of z mean, and then minus tf dot exponential and z underscore log. This was the formula for KL divergence loss. The total loss will be the addition of these two: reconstruction loss and the KL reconstruction loss, as well as the KL loss. Now, how do we define the gradients? So we can use this type variable. So we can define the gradients. Grads is equal to tape dot gradient. Tape dot gradient. We will be calculating the gradient for this total loss with respect to all the trainable parameters here. So we will pass on this total loss as input to this gradient function, and we will also pass on self dot trainable weights. So the trainable weights of this particular class will be passed on here. So basically, this step is calculating. So what we are doing here is, this function is only one step of training. So in each step, what we are doing, we are inputting the data to the encoder. We are calculating the latent attribute, passing this latent attribute to the decoder, and computing the reconstructed input. Now, with this reconstructed input, we are calculating the loss, and try to recall, we had two terms in the loss function. One is the reconstruction loss component and the KL divergence loss part. So we have computed reconstruction loss using these formulas and the KL loss. Finally, the total loss will be the summation of these two losses. Now, the next step is to find the gradients of this total loss with respect to these weights. And then we will optimize using the back propagation. So we will be using the optimizers. So self dot optimizer, self dot optimizer dot apply gradients, and then we will pass on the calculated grads, and we will pass these trainable weights, self dot trainable weights. So this optimizer will optimize, self dot trainable weights. So this optimizer will apply the gradients on this gradient calculated here with respect to the training uh, weights, and then update the state of each of. So basically what we are doing here is we are implementing the complete training algorithm ourselves here inside this function itself. So each step is doing the training process. Now we are, once we have calculated these gradients, now we will update the values of these weights. So self dot total score loss score tracker, and then update the state, pass on the total score. And finally, as a return to this function, just return uh, the loss, and loss is what we have calculated here. It is self dot total underscore loss underscore tracker, and what is the result of this? Result as return to this function. Fine. So what we have done, we have built a class, a VAE model, in which we have the compile and the training step itself. So let us run it. Let's see if there is any problem here. Yeah, if is instance data tuple. Yeah, fine. So we will require I think we can run it. Again, there is some error. Module TensorFlow has no attribute Kera. I think I wrongly typed Keras as Kera. Class VAE, yes. The beginning itself, I do the typo mistake. Now let us run it again. Fine. Now this is successfully built. This VAE is successfully built. Now the next step is to use these functions, these models on the data. So what we are going to do here is we will train the model. And how do we train this? We will call build score coder. So basically what we are doing, we are making an instance of these. So write a command, train. Similarly, sorry, typed it. Then similarly, we will have the coder or build coder. Now we have to define the object of this VAE and try to recall what we are passing to this class. We are passing models as input, encoder and decoder. So we have defined the instance of these two functions, encoder and decoder. Now we will pass this encoder and decoder to the object, create the object of this VA class. As an argument, we will pass these. You can straight away pass these functions as well. But just for better readability, we are passing these examples. So Now we have created an object of VAE. Now through this object, we will call this compile function here, and then we will call the training function here. So VAE dot compile, and inside compile, you can see what all arguments we have to pass. We have to pass the value of the optimizer. So what kind of optimizer we are going to use, that we need to define. So optimizer, uh, we will use the Adam optimizer. So tf dot uh, tf dot keras dot optimizer, tf dot keras dot optimizer dot, and once we have compiled this particular model, next can be next could be fitting the model. So VAE dot fit, and we pass training data. Remember, we are not passing the Y train because it's unsupervised one, so we do not need this. And then we will define number of epochs, though it requires at least 100 epochs, but every epoch is taking almost 1 minute to run. So I'll only use 5 epochs here just to demonstrate. Also, I can define the batch size. I can define the batch size as 128. So next is uh, what we have done till now. We have built the encoder. We have compiled it, and then we are going to train. So let us run it. So there are some errors. Yes. What is the error? Unrecognized keyword arguments passed to on P2D, and it's in the function build encoder. So at the earlier time when we defined this build encoder function, it didn't give us this error. Now it's a runtime error when we are calling this function, and I think there is a problem here. We have used stride instead of strides. That we have to correct. So basically we need to run this again, build encoder. Fine. So let us run it again. This time, yes, this time the problem is with the decoder function, and inside this decoder function it says it has no attribute reshape. Let me see what's the problem we have done in the decoder one. This is reshape. Could be the error here. Yeah, it's a typo mistake. I think this could be capital. Fine. So let's run it again so that we can use it there on training. So let us run again. Now this time we are having some problem. Takes 2 positional arguments, but four were given. Two positional outputs, 1, 2, 3, 4. But 4 were given. I think there is some issue here. We'll see. Inside reshape itself, it is giving us some problem. Yeah, fine. So we have to define this shape inside the brackets in the reshape function. So this always we define the shape in these brackets. We can call that. Let's run it again. I hope this time it will run. Next. Fine. So TensorFlow Keras has no attribute optimizer. It will be optimizers. Optimizers. And then I think Adam will also be capital. Yes, Adam will also be capital. Let's run it again. Yes, still there is some problem. And that problem is, I think we missed a dot here. So this is in the compile function keras dot matrix. Let me run it again. And run this training code again. Still we have problem. Can someone guess what is this problem? Open to the audience. Can someone guess what is the problem here? It should be epochs instead of epoch. Now let us run it. Yes, this time again it is giving us some problem. What is this problem? TensorFlow has no attribute reduce. So it is in the train step, I guess. So let me go back there. This might be the problem. Fine. So it was not tf dot reduce underscore mean. Not reduce dot reduce underscore mean. I think fine. I hope this time errors will be resolved. So let me run it again. No, still there are problems. Fail to convert elements to function binary cross entropy to tensor. Consider casting to a supported type. I think so. There is some problem here. In terms of function binary cross entropy, I think this will take consider. Let me see if this time it works. And then we will have to pass on inside this binary cross entropy. We need to pass on the loss function for which we are computing this. So Just give me a moment. Let me see what arguments we have to pass here. Uh, Basically, it says that we should pass the y true and the y predicted. So basically, the output of uh, this model, and so basically the reconstruction loss, there will be input data and I guess the reconstruction is the output here, and data is the input to this encoder. So that we should pass this here. Let me see if it works. Now it says this Adam object has no attribute apply gradients. I think it's underscore apply underscore gradients. There are so many typos on my side. I'm sorry. Uh, Again, there is some error. This apply gradients takes two positional arguments, but three were given. So apply underscore gradients. Yeah, fine. So I think I did this mistake. Again, there is some problem. This was a spelling mistake. Total loss tracker. This is a return. Total loss tracker. Yes, finally we have reached to the training stage. I'm sorry, there were some typo mistakes. So meantime, when this training is going on, you can complete the code if you have not completed. Let me uh, put the screen in this manner. Please let me know which portion you are not able to complete. What I can do is I can write uh, code till here in the chat, and maybe you can use that code and paste it. And the last two lines are not copied here, so I'm copying them back. So I think there was a majority of the issues in this particular class VAE, so you can use this code directly. And Those who want to take screenshot here, they can take a screenshot and then change their code or complete their code accordingly. Or encoder and decoder model. So as of now, two epochs are complete. I mean, second epoch is going on, and you can see the loss in the second epoch. Yes, we are able to reduce the loss. Now the third epoch has started. I hope everybody is able to complete the code till here. If any one of you facing any problem, please let me know. I can help you with that. So meantime, when this training is going on, let us write the further code. So now next we are going to visualize the latent space, which we have seen in the previous session. So let's write function for visualization of latent space. And let us say this function is def. So this name of this function maybe port latent space. And of course, we are going to pass the object VAE for the input data, the actual label of the data, and number of samples. So we are passing only, let's say, 5,000 samples instead of 10,000 test samples. So we'll have color coded digits. For each of the digit, we'll have latent space depicted with different color. Now we'll find out this new column. Now the indices p dot random dot choices, and the we need to define the length of the data. Then we consider the number of samples, place them. The default is true. False is character. Fine. Then the data subset is equal to the data indices, and similarly the label set So what we have done here is, since this data is of full dimension, the complete testing data is here. We only want to have 5,000 samples out of it. So what we have done, we have defined indices. Out of this total length, we are just sampling 5,000 of them and considering this subset, uh, taking out this subset from the whole data, and we have indices for them. And similarly, we will have label for each of the image here. So for visualization. Now, firstly, what we are going to do is we are going to encode this input data. So we know how do we encode? We use the encoder. So encode the data to latent space. So since we are plotting the latent space, so we need to encode the input data to the latent dimension. So how do we encode it? We get Z mean, we get Z underscore log underscore there, and also we get Z. What do we pass here? The VAE, since we have passed the object of this VAE class. So VAE dot encoder, we are going to try to recall. We called encoder function inside the VAE class. So we have that instance of that encoder inside this class object. And what are we going to pass? We are going to pass this data subset here. So this basically, this line will calculate the latent representation of this data subset. And then we will convert this output to NumPy array, because this encoder will give us uh, tensor output. So basically, we will convert this Z underscore mean, so we name it NumPy, Z mean NumPy, because it's a NumPy version of this tensor output. So Z underscore dot NumPy is the function, convert it into NumPy format. And now let's create the scatter plot. To recall our discussion in the morning time, see a similar kind of scatter plot here. Our training has been completed for after 5 epochs. Still, the loss is very high. As I was telling you, we will need at least 100 epochs to train this completely and to minimize the loss. But we will see just for visualization, we will see how it has performed. Now, let's create a scatter plot. So we will define a figure, TLP plot of figure, and the size of the figure. Some of code is similar to what we used yesterday. 8 cross 8. And now let us define the scatter plot. Maybe scatter is equal to D. And this library, this matplotlib library, has a scatter function called scatter, which can plot the input data as a scatter plot. Now, what exactly we are going to pass here? Z mean in empty format. You remember we calculated this. Oh, I think it was NumPy. Let's use it NP for a bigger name. So Z underscore mean underscore NP, and we will take this 0th distance, and I'll ask this question to all of you: what we are doing by writing in this manner P. Then can anyone tell what exactly we have done here? C is equal to labels underscore subset C R is equal to 10 10, and these are the parameters for the scatter plot alpha. Let's take it as 0.6, and another parameter as equal to. Don't bother about these parameters of this scatter plot. So basically, what we have done here is uh, there are two dimensions. If you can recall, there are two latent dimensions. So basically, there will be mean for both of them. So we have taken both of them, 0th and first dimension, and that we are plotting on a scatter plot. And we are considering these labels since there are 10 labels. So we will use different color coding for these labels. And I think we can use the color bar. We need to define the color bar, display the color bar. So this color bar is for different digits, 0 to 9. So this inside this scatter itself, it should show the color bar, and the labels. The label will be, of course, the class of the digit. Class. Fine. And if you want to define the name of the axis or the X label or the Y label, LABL. So on the X side, it will be latent dimension 1. Similarly, we have Y, we have latent dimension 2. Is fine. And I think we need not to give title to this plot, and definitely we want to see the grids. We will make it true. So plot dot grid should set the argument called alpha for this, so to define the value for this. And then finally plt dot. This is the function which we have defined for visualization of the latent space. Now let us call this function, because this is just the definition. Let us call it. How do we call it? That's the name, plot underscore latent underscore space. And what we need to pass the object of VAE, and of course the data. Name of the input is data, not data. We need to test it on X test. And what is the label for Y for test? It is Y test. So what exactly we have to pass here in this function, the object of the VAE, so that we can call the encoder and the decoder function. The input data. So here we are plotting the latent space for the test data, and we need to pass on the corresponding labels. And we have already defined for how many samples it is going to do this visualization. So let us run it. Again, there is an error, plot latent space. The error is module numpy.random has no attribute choices. Choices could be, I think there is some spelling mistake again here. It is not choices, it is choice. Sorry. Again, let me run it. Again, there is some error. Name labels subset is not defined. Again, we have made so it's label subset rather than labels subset. Let me correct it. Run it again. Oh wow. So what exactly we have got here? Since the training was not complete, training was not perfect, we have not got the smooth or continuous distribution. It is intermixed. But had it been for 100 epochs, you could have got very smooth and continuous distribution of the data. Continuous distribution of the data. Fine. Fine, I guess. So this was the distribution of the latent space, visualization of the latent space. Now what we are going to do is, let us see how our variational autoencoder has reconstructed the output. So we just want to display the reconstructed outputs. So let's write a function that will be the last function of the set diagram. Let us write a function for that. So that function will be def float construction comparison. I'll do it quickly because we are running out of time. So comparison, and here also we are going to pass VAE and data, and we'll do it only for 10 samples. 10 samples, and inside this function we will plot. We will do it for. We will do it randomly. We will pick 10 random samples. So again, we will define the indices equal to np dot random dot choice, and of course the same function which we have used earlier. So it will be len data, and out of that len data we are just sampling n samples, that is 10 here, and then it is equal to fine. Then original will first we take the original images. The original images we will just take it from the data and use these indices. So only 10 images we have put in this, and now let's get the reconstruction. So reconstruction will be z underscore team comma z underscore log comma z, and we will feed these original images to VAE dot encoder original images, and then we'll pass this z to we computed using VAE dot decoder, and we will pass z as input to this decoder. So now we have original images, and again we have the reconstructed images. So now let's run a for loop. Firstly, let's define a figure plot dot figure, and the fig size is equal to 20,4, and let's do it for all n samples for I in range, I in samples. And what are we going to do here is we are going to plot. So plt dot plot The subplot is of dimension 2 cross and I plus 1 TLT dot IN show. We will show the original image at ith index, and of course we need to reshape it. Reshape it in the original dimension 28 cross 28 because it was in dimension 28 cross 28 cross 1. We have to reshape it, and the CMAP will be dot digital. It's the original. Similarly, we can plot the constructed. So let us copy this for loop again. I mean, not for loop, the subplot again. So here also we have I plus 1 plus. So after plotting these original ones, we will plot that they directly comes below the original ones. Here, instead of original, we will have reconstructed images and reshape it to the same. And of course, we'll do one more thing. We will convert them into NumPy format for reshaping them. So NumPy and then reshape them. 28 cross 28, and this one is reconstructed. Reconstructed, and then ELT show. Sorry, it is in the for loop. We have to come out of this for loop. And once we have defined this plot reconstruction, we will call this function underscore reconstruction comparison. We will call this function and pass to VAE and the underscore. So I think let's run it. I'm sorry, I think we have not put it outside this one. So let us stop it. Now this is what we have got. Some of them are correctly reconstructed, but they are blurry versions because we have not trained this model properly. So I think that completes our experiment here. If you, we will share this notebook with you, and I request all of you to please train this model for 100 epochs and then see all these visualizations again. So I think let's conclude here. If you have any queries, please let me know. I can address those queries. Yeah, of course, there will be indentation errors when you are doing coding in Python. So please show the last cell. This is the last cell. So since we are running out of time, I'll share. Let me do one thing. Let me copy this in the chat itself so that you can use it directly. And use it here. So with that, let me conclude this session. Thank you, and you'll get information on the chat regarding the next session. Thank you. Thanks a lot.